need to do are the ones with perfect cubes. We've done perfect squares before, and that was just, you take the square root of the first plus the square root of the second, the square root of the first minus the square root of the second. But now we're going to do perfect cubes. Okay, and when we do perfect cubes, it has to be, the first one has to be a cube, and the second one has to be a perfect cube. If we have that, we can follow a formula. Okay? The first formula is for the difference of perfect cubes. All right? And this formula you do not have to memorize. It should be on your formula sheet. So we have it right there. What we do is we need to figure out what A and B are. A and B are the perfect cubes. So, what is the cubed root of r cubed? That's what A is. A is equal to r in this case, because r times r times r is r to the third. What is the perfect cube of 125 q to the third? So, what times itself 3 times is 125? That's what B is. 5 and q, because q times q times q is q to the third. Now that we know what A and B are, we can just follow this happy formula right here. So we start with A minus B. A is R, B is 5Q, so we just write R minus 5Q. Then we're going to go and do the second part, which is R squared, because A is R, so we're going to write R squared, plus, now for the second one, we're going to multiply A times B. So 5 cubed times R. So we'll write 5R cubed. Doesn't matter if it's 5QR, 5R cubed. Then the last part is the B squared. 5Q squared is plus 25Q squared. Now we can look and see, could we factor either of these? The first one, obviously, no. The second one, does anything multiply by 25 but add to 5? Nope. So put a box around it, you've factored it. Let's try the second one now. And with the second one, we have the sum. So we cannot do the sum of perfect squares, but we can do the sum of perfect cubes. The sum of perfect cubes, we just have a slightly different formula where the addition and subtraction of the plus and minus are in different spots. Otherwise, exactly the same. Perfect cube of y cubed is y. Perfect cube of 27, that's going to be our b. That's 3. Okay, so now we just follow the formula again. A plus b, so y plus 3. And then we have to follow this part. Put our parentheses, do a squared. So we substituted y in for a, so that would be y squared. And then a times b, so y times 3, which is plus 3y. And then b squared, which is that number squared, plus 9. Again, look at it to see if you can factor again. It doesn't look like you can because nothing squared, or nothing times, or there's nothing that multiplies to be 9 but adds to 3. So that is our answer. Now sometimes we get to ones that are a little bit more challenging. So we have x to the 6th minus 64. So x to the 6th minus 64 is our next problem. So we need to figure out, this is a difference. So we're going to figure out what a is. A is what times itself 3 times is x to the 6th. So a in this situation is x squared. And b is what times itself 3 times is 64. Notice we don't concern ourselves with that right now. That just tells us what formula to use. All right? So b is 4. Now if we follow our formula from the formula you have on your sheet there, it is a minus b. So x squared minus 4. And then it is a squared. So what is x squared? I think that's x to the 4th. And then a times b, so that would be plus 4x squared. And then b squared plus 16. And I'm just following the formulas with the addition and subtraction. Now when I look at these, again, I can look at the first one and say, can we factor x squared minus 4? Now we can, because this is a difference of perfect squares. So you have to be really strong with your factoring, but x squared minus 4 is x plus 2 times x minus 2. We should check the second factor to see, is there anything that multiplies to be 16 but adds to be 4? Nope. So then we have this is our final answer. There are actually 3 factors when we break it all the way down. All right, so that one's a little bit tougher. Let's try one other one. And let's do y to the 9th plus z to the 9th. Y to the 9th plus z to the 9th. Just trying to make sure we've done all the tough ones. So y to the 9th plus z to the 9th, we would first figure out what y is, or what a is. A is equal to, what times itself 3 times is y to the 9th? Y to the 3rd. Y to the 3rd, y to the 3rd, y to the 3rd gives you y to the 9th. And b is going to be z to the 3rd. Okay? So in order to do this one, we would have a plus b. So that would be a, or y to the 3rd plus b to the 3rd. All right? That's going to be our first one. My fault. Z to the 3rd. I wrote b in there for some funny reason. Plus z to the 3rd. And then we'll do the next part, which is a squared, so that's y to the 3rd squared, which is y to the 6th, minus y to the 3rd times z to the 3rd, and then z to the 6th, because it's b squared. So we have z to the 6th as our final one. We end up with that. So we can look at this and say, could we factor y to the 3rd plus z to the 3rd? Oh my goodness, yes we could. That's a sum of perfect squares again, or perfect cubes. So now in this one, we have a equals y and b equals z. So we have to factor that one out all the way again. All right? So when we do that, we would get y plus z times, now we need to do y squared, following the formula, minus yz plus z squared. That is this one factored again. The last one, the 6th, we cannot do that because we can't figure out something that multiplies to be z to the 6th and adds to be negative y to the 3rd, z to the 3rd. So our final answer would look like this. That is why this one is so spicy. It actually, you have to do sum of perfect cubes twice. So after a little bit of practice, this will get easier, but these ones where you factor twice, they're a little bit tougher, definitely. Good luck.